Before 1922, hitting a high-pressure pocket often meant the Earth simply emptied itself into the sky. Without a way to bridge the gap between the reservoir and the surface, these gushers routinely destroyed the wooden derricks and the crews working them. The fundamental risk of drilling is that you are piercing deep into the crust, intentionally creating a path for gas and oil that has been trapped under thousands of pounds of pressure for millions of years. Containing that force requires a specialized assembly of high-pressure valves sitting in the cellar directly beneath the rig floor. This is the blowout preventer, or BOP. It functions as a vertical stack of independent barriers, each designed to provide a specific type of seal against the wellbore if primary control is lost. By capturing and mechanically containing that pressure, this stack turns a potential explosion into a closed hydraulic system that can be managed and neutralized from the surface. The design relies on redundancy. Much like an airliner using 3 independent hydraulic systems to ensure no single mechanical failure grounds the plane, the BOP uses multiple valves and duplicated control panels located across the rig. The topmost layer is the annular preventer. Inside the steel dome is a thick rubber packing unit. This is the first valve closed when detecting an influx. Hydraulic fluid forces a piston upward, squeezing the rubber element. It moves inward, closing like a camera iris. This valve sits on top because it seals around anything. It conforms to a thick collar, a thin wire line, or keeps squeezing until it seals an entirely empty hole. This flexibility allows the crew to gain immediate control of the well pressure, regardless of what equipment happens to be passing through the wellhead at that moment. Beneath the annular are the pipe rams, providing a hard, long-duration seal. Unlike the flexible rubber above, they use heavy steel blocks sliding horizontally. Because they are rigid, their semicircular cutouts must precise and match the specific drill pipe to form a seal. At the bottom is the shear ram. This valve uses hardened steel blades to slice through the drill pipe and seal the wellbore entirely. If the shear ram provides a complete seal instantly, why isn't it the first valve the driller closes during a kick? Severing the pipe causes the entire drill string to fall to the bottom of the well. This creates a massive recovery operation and often requires the rig to abandon that section of the hole. Closing the BOP stack is only the first step. It holds the door shut, buying time for the crew to circulate heavy mud through a separate manifold to kill the well and permanently neutralize the pressure. The shear ram is used only when those other options have failed, as it involves an intentional choice to sacrifice the well to protect the lives on the rig above it. The difficulty with any emergency failsafe is that it spends nearly all of its life doing nothing. A BOP stack can sit idle for months, yet it must function perfectly within seconds of an alarm. To address this, API 5.3 regulations mandate that this equipment be pressure tested at intervals not exceeding 21 days. These tests follow a specific sequence. Before the crew runs a high-pressure check, they must first prove the stack can hold at a low pressure of 250 to 350 psi. The reason for the low-pressure start is that extreme pressure can actually hide a leak. High pressure mechanically energizes the rubber seals, squashing a degraded element against the steel and creating a temporary seal that disappears as soon as the pressure drops. If a seal is going to fail during a blowout, it is often in those first few moments before the pressure peaks. A gauge reading full pressure at the end of a test means nothing if the seals haven't been proven in their weakest state. The hardware may stand 20 feet tall and cost millions of dollars, but its ability to function is only as certain as the last time a crew proved it could hold.